Hello, ladies and gentlemen, and welcome back to more, or should I say the end of, the 2016 Intermediate Contest. That's right, we're on B3, the very last question in the contest. We can see we've got 4 things to work out. We're going to have to write up our answers for each part. And question 3, let's dive in and take a look. For each positive integer n, the Murray number of n, I wonder if you actually sort of Google Murray number, if something comes up, or maybe Murray's the guy who made up the question. I don't know. Murray number of n is the smallest positive integer, capital M, with m greater than n, for which there exists one or more distinct integers greater than n, and less than or equal to m, whose product times n is a perfect square. What? For which there exist one or more distinct integers greater than n, and less than or equal to m, whose product, the product of that integer or those integers, times m, and then times n again, is a perfect, I don't know. Let's look at their example. For example, the Murray number of 3 is 8, since 3 times 6 times 8, so 6 is our number less than or equal to capital M and greater than n. 3 times 6 times 8 is 12 squared. And it can be shown that it is not possible to multiply 3 by one or more distinct integers that are greater than 3 and less than 8. Oh, now you're saying less than 8, but not less than or equal to. What? To obtain a perfect square. Okay. This is a very weirdly worded question. So, one or more distinct integers. Less than or equal to m. So, I think what it is I take a number like 3 and sort of I ask for some distinct integers that are greater than 3, whose product with 3 all gives me a square, and then the biggest of those numbers becomes the Murray number. Or, no, we take our 3, and then we take all possible sequences of one or more distinct integers that are bigger than 3, whose product gives me a perfect square. And the Murray number is the largest number in the shortest or smallest of those sequences. Yes. Okay, I think I've got it. That is really weirdly worded. I don't know. I can't remember if there were any difficulties in marking this one. I don't know. Some of the people doing these content, you might have read this and had no problem with it, but that's weird. Okay. The Murray number of 6 is 12. Show why this is true. If we're thinking about arbitrary runs of numbers, then I'm inclined to think factorials might come in here. Anyway. The Murray number of 6 is 12. Show why this is true. Okay, so first I should show that it is a Murray number, or it is a potential Murray number. That is, I can do 6, 12, and something else, or maybe some other things that are less than or equal to 12, and get a square, and then I got to show why you can't do it with more stuff. Okay. So first things first, we got to find some other numbers along with 6 and 12. So okay, let's get into this. So I'm going to give a definition just so that I'm clear as to, when in doubt, when you think you're trying to interpret a question and there's multiple ways, a great way to start things off is to say, this is what I think is going on with the question. It helps it doesn't always get you part marks because some people just say, no, you're wrong, you interpreted it badly. But I'm going to start off by giving a definition. For a number n, a number little m greater than n is called Murray-like. I tend to underline the term we're defining. If there are one or more distinct integers n less than a1, a2, yada yada yada, less than or equal to m, so that n, a1, a2, yada yada yada, all the way up to ak is a perfect square. Okay, so then I can make the observation the Murray number of n is just the smallest Murray-like number. Okay. So, this is my understanding of how Murray numbers works. And now I can talk about numbers that satisfy the condition of being a Murray number, but aren't the smallest. So these are my Murray-like numbers. I don't know if this is actually going to be useful, but it helps me organize my thoughts. Okay, maybe we'll need to talk about Murray-like numbers. So for A part, first let's show 12 is Murray-like. So that means it satisfies the conditions, and then we're just going to have to rule out 11, 10, 9, 8, and 7. Okay? So 6 times, well, it would have to be with 12. Do I need anything else in there? So 6 times 12 is already 72, which is 2 cubed, 3 squared. So the 3's are accounted for. We don't need any more 3's. Although you could add in, I guess, 9 and it wouldn't change a thing. But we've got, so that's 2 times 6 squared. So we need an extra factor of 2. So let's think, what even numbers could I add in? Well, between 6 and 12, there's 8 and 10, and that's it. So could I add in 10? Well, that would give me an extra 2, but it would also give me a 5. And then I'd have an extra factor of 5 sitting around, and I'd need to pair that with another 5 in order to make a square. So it looks like 10's out, but we can go with 8. Okay? Because 8 would introduce 3 extra factors of 2. Pair that with 1, suddenly you've got 4. And an even number of 2's is a square. Okay? So, I don't think we really need to motivate this at all. But 6 times 8 times 12 is equal to 36 times 16. It'd be 24 squared, I think. Right, because 12 and one of those 2's gives me a 24, and then the leftover 3 and 8 gives me a 24. Notice that we can also do this one. And that would give us an extra 3 here, so that'd be 72 squared. You don't have to, but it does show you that there are multiple ways to show that 12 is Murray-like. Either one of these will suffice. So observe either of those. So 12 is Murray-like. Now we just need to show that 11 is not Murray-like for 6. It's not, and 10 is not. 8, 6, 9, 8, 7, and so forth. Okay. I have a feeling prime factorizations are going to come into this a fair bit. So What's the best way to do this? I'm trying to... Do I go about it with prime factoring, or do I just show that none of this is going to work? Let's make a chart. So we'll try the other numbers. So try m being 7. So what products could I have? Well, I could have 6 times 7 is really the only one, 42, and that's not a square. How about 8? Well, you could have 6 times 8, 48, and that's not a square. Or you could have 6 times 7 times 8, and that's also not a square. What number is that exactly? 42 times 8, you get a 6, carry the 1. 336, not a square. So you can sort of see this method here is going to run into some problems. Now the 9 one you can rule out right away because you can either have 9 times 7 or 6 times 9 times 6 times 7 times 9, which is 9 times 42, which is not a square because 42 was not a square. Or you can have 6 times 8 times 9, which is 48 times 9, also not a square. 6 times 7 times 8 times 9, this is why I'm thinking factorials will come into it, and that's 336 times 9. So 9, perfect square, he has to use other numbers smaller than it. So I think you can never have, so this is just an observation based on the 9. Maybe no square can be a Murray number. Unless, I think part of the definition is you have to have at least one integer. So unless n is a perfect square. And even that might fail or something, I don't know. But notice that 9 didn't change it. We still get these other factors in here, and since they're not perfect squares and 9 is, the result can't be a perfect square. So we've got 10 and we've got 11 left to do, and these are going to get ridiculous. I mean, I'm going to have to grab my calculator. So we ask ourselves, is there a faster way to do this? And so I say, if 10 is the Murray number, then 6 times 10 times some other stuff, maybe, is a perfect square. So that means 5, which divides 10, which divides 60, which divides k squared. 5's got to divide k squared, so 5's got to divide k, because it's a prime. So we need another factor of 5 from somewhere, but there's no number, there's no factor of 5 between 6 and 10. You get 7, 8, or 9. None of them are multiples of 5. Similarly with 11, introduces a factor of 11 that we just can't deal with. So that rules out 7, 8, 9, 10, and 11. Of these methods, I like the looking at primes and saying, well, you got one 5, you've got to pair it with another 5, and there is no other 5. I like that. That's a little slicker than just working out all the possible combinations. But either way, as long as you sort of explain what you're doing, fancy this sort of chart up. By the way, the same explanation will work with 7. It's just 8 and 9 that are a little more finicky. But either way, we sort of just put some sentences in there, and that shows that 12 is really the smallest number that's Murray-like, and therefore is the Murray number. Okay? So I'm going to leave A there. Of course, you can jazz it up. interesting observations. Prime numbers, prime factorization seeming to come into it a bit. And my observation about 9 isn't the Murray number because there might be smaller stuff. I suppose I didn't try 6 times 9. But of course that's 54, and that just is also not a square. Because 6 is not a square. So if we had something like the Murray number of 4 is probably 9, maybe. Things to think about. Anyway. So that's A part. Now let's take a look here at B. Determine the Murray number of 8. No justification required. Interesting. Okay. So we're going to have to, I guess, experiment a little bit. And, yeah. Murray number of 8. So we start thinking about prime factorizations, I guess. So 8's already contributing a 2 to the 3. And so we need at least another even number in there to give us another 2. And then, so what even numbers could we add? How about 10? Well, that's going to introduce a factor of 5. Then we have to go hunting for another factor of 5. So it's going to be interesting how we chase this stuff down. And we can work it a little bit. So 8 is 2 cubed. We need another factor of 2 to make a square. And if you're feeling uncomfortable with this, of course, make the side observation that when it comes down to prime factorization, so when we have any number like this, when we write it with prime factorization, where P1, P2, and so forth are distinct primes, you make the observation that this is a square exactly when E1, E2, and EK are even. Okay, so this is the basic fact that I'm using. If you want to, write it down somewhere in your solution, but I would say it's obvious, so I wouldn't dwell too much on it. But so we need an even number of factors of 2 here. Okay. So how about 8 and 10? Well, that would give us 80, and that's 2 to the 4 times 5, so we'd need a factor of 5. And so that would lead us to at least 15, and then that would give us an extra factor of 3, and since 15 is the highest, then we're assuming 15 is the Murray number, and you can see it's sort of spiraling out of control. 8 and 12, you're going to get 2 to the 5 times 3, so not only do we have an extra 3 to deal with, but there's still an extra 2 kicking around. So no, not good, not good. How about 14? Well, you're going to have sort of the same problem. You get 2 to the 4, but you're also going to get a 7. You need another 7. Big problems. How about 16? Well, you got 2 to the 7 there, and so that still needs an extra 2. Okay, so not good. How about 8 and 18? Well, here we go. So the 2 there, we get 2 to the 4, and we've got 3 squared already built in. This is a perfect square. Specifically, it's 12 squared. Okay? And I would say this is actually pretty good justification. Okay? So you need another 5. That would lead us to 15, which needs another 3. And so you're going to have to go to at least 18. So 18 would be at least the Murray number there. With the 12, then you need to go to another factor of 3, and that leads you to 15, to another 5, and that leads you to at least 20. No good. 18 beats it. For this one, we need another factor of 7, so that we get a Murray number of at least 21. That's not going to work. Here we need to at least 18. And actually, this one with 18 will also give us a Murray number. So 18 really is our best. And you can, again, add some more sentences describing it, but they said no justification, so just getting a final answer of 18 would work just fine. All right, not a whole lot of observation in terms of Murray numbers that I can make there, although I guess 2 times a perfect square there is what helped us out because we had all 2's. All right, so we'll flip the page in anticipation of our next one. C, prove there are infinitely many positive integers n for which n is not a perfect square and the Murray number of n is less than 2n. Okay. Alright. So we can't have n be a perfect square. Fine. Not a big deal. Usually the way they structure these questions is that A and B will help you get introduced to this concept of Murray numbers, and C and D then ask you to develop some theory here. So I would guess that we have an example of what we want in either 6 or 8. Now, 8's Murray number, we said, was 18, which is more than twice 8. Okay, so, not so good. But 6 has a Murray number of 12, and that's exactly 2n, so that's also not quite working. All we need to do to answer this question is to show that there is a Murray-like number that is less than 2n. Because all Murray-like numbers are bigger than or equal to the actual Murray number. That's an observation we can make. A fairly quick one. Because the Murray number is just the smallest of all Murray-like numbers. So if you have a Murray-like number, by my definition, that is less than 2n, your Murray number will have to be less than that, and therefore also less than 2n. Well, less than or equal to that, and therefore less than 2n. So we just need to find a way to get Murray-like numbers, and I think this 8 and 18 might be sort of the prototype, the thing that we want. So I'm thinking maybe odd powers of 2. So let's explore that for a moment. So I'll write down my observation. No, we'll write it down at the end when we actually finish the proof, assuming that this works. So let's try n is equal to 2 to some odd power. Now we can write odd numbers in a very nice way, 2 to the 2k plus 1. We need a factor of 2 to make a perfect square. Okay, now what I want is, so twice n, by the way, is 2k plus, so it's another 2, so 2k plus 2. Alright, so what I need something that is, so we would like an m which is 2 times a perfect square. Let's call it, I don't know, t squared. So that n is less than m is less than 2n. Okay? So if we can show that there's an infinite number of n's, n being 2 to the odd power, so that there is these 2 times perfect squares, then we'd be all set. Since nm would be 2 to the 2k plus 2t squared, which is a perfect square. So m would be Murray-like for n. And so m, the Murray number, of n would be less than this m, less than or equal to. So I just need to show that enough of these 2t squareds exist. And this is my generalization from 8. How did we get 8 and 18? 18 was 2 times a perfect square. Okay. Now, unfortunately for 8 and 18, 18 happened to be bigger than 16, which was 2n. But I'm betting if we do something like 32, we can get twice a perfect square between 32 and 64. For example, 50. 50 would work just fine. So I'm betting this will work for really any 2 to the odd power other than 8. But we've got to show this. We've got to show this. So if 2 to the 2k plus 1 is less than 2 to the t squared is less than 2 to the 2k plus 2, we divide by a 2 on both sides. We get 2 to the 2k is less than t squared is less than 2 to the k plus 1. Okay. Now I need to show that there's a perfect square in here. Is that an obvious thing? So this guy right here is 2 to the k all squared. So let's let t be 2 to the k plus 1. Then I'm thinking we can show that it's unless k is equal to 1, we should be all set. Now, 2 to the k is less than 2 to the k plus 1. So 2 to the k squared is less than 2 to the k plus 1. So the plus 1's down below. All squared. And that's 2 to the 2k plus twice 1 times 2 to the k plus 1. It's 2 to the 2k plus 2 to the k plus 1 plus 1. And this guy here is 2 to the 2k. So we need to show 2 to the k plus 1 squared is less than 2 to the k plus 1 for an infinite number of k. Because then we get an infinite number of n's. None of these are perfect squares because it's 2 to an odd power. Okay, 8's not a perfect square. 32, not a perfect square. And you might want to mention that that's why these 2 to the odds should work. But, okay. So now we've got 2 to the 2k plus 2 to the k plus 1 plus 1. I want u to be less than 2 to the 2k plus 1. Alright, so this is twice 2 to the 2k. So I can subtract off a 2 to the 2k from both sides. So I need to show 2 to the k plus 1 is less than 2 to the 2k. Okay. So I need to show that 1 is less than 2 to the 2k minus 2 to the k plus 1. I can take out a factor of 2 to the k plus 1 here. Well, let's just take out a factor of 2 to the k. And I'll be left with 2 to the k minus 2. And so 2 to the k is always greater than or equal to 1. 2 to the k minus 1. So for all k greater than or equal to 0. And so we just need 1 to be less than 2 to the k minus 2, which is 3 less than 2 to the k, which is true for k greater than or equal to 2. Okay. So putting that all together, so to summarize, for k greater than or equal to 2, if n is equal to 2 to the 2k plus 1, an odd number, so i.e. n is not a perfect square, then m equals 2 to the k 2 to the k plus 1 2 times 2 to the k plus 1 squared. Has the property that nm is a perfect square, and so it's Murray-like. So the Murray number of n exists and is less than or equal to m, because at very least little m itself has to be the Murray number if no other smaller one exists. So the capital M exists and must be less than or equal to m. And our final observation, n is less than m is less than 2m, or 2n. So then m has to be less than 2n. So we've got a Murray number. This little n isn't a perfect square, and I know that the Murray number has to be less than 2n because I've got a Murray-like number that's less than 2n. And that's a fancy way of saying I'm done. So there we go. That was just C part. Not so bad. Having done B part and 8, we sort of get that nice quick connection with 8 and 18. You might be discouraged from it because obviously 18 is more than 16, but it turned out it all worked out fine. I'd be interested to see if there's a more general way to do it, or if their solution used another class of numbers. I mean, I very much doubt that it's got to exactly be 2 to the odd, starting with 32. There's probably other numbers that do it. Maybe there's another family we could find out. Okay? So, if you want to read their solutions, of course, my second link takes you to their general past contest website, and you can read their solutions for yourself. Okay? But we're not done. We've got D part. Okay? So let's take a look at D. Prove that for all positive integers n, the Murray number of n exists. Okay, so I talked a little bit about that there in the end of my solution to C. The Murray number of n exists and is greater than or equal to n plus 3. Okay, greater than or equal to n plus 3. So there's two parts to this. We need to show that Murray numbers exist, and another side thing that no number smaller than n plus 2 can be the Murray number of n. Okay, and then you can tackle it two different ways. I mean, if you're a little unsure of how to show whether or not a Murray number exists, I mean, an idea just popped into my head, but maybe you're a little slow on that part. You don't have to show that the Murray number exists to then say, well, if I could show they exist, let me show you that it's not going to be n plus 1 or n plus 2. Okay? You can automatically just jump to that if you can't show that the Murray number exists. Or maybe you can show Murray numbers exist, you just can't quite do the showing that it's got to be at least n plus 3. Okay, there's two things to unpack here in D. Both of them are worth marks. If you can't tackle one, try and tackle the other. Okay? So, alright. Which do I want to go for first? I think I'll show, because I just had an idea as to how to show Murray numbers exist. I will flip the page, and I will talk about showing that Murray numbers exist. So, it is enough, or it suffices, to show that for any n has a Murray-like number. I actually wonder how you would do this if you didn't have the definition of Murray-like numbers. So I'm glad I made that decision to define that at the start. For any n has a Murray-like number, m. Since if there is no smaller m that is Murray-like, then m is the Murray number. And if there are smaller Murray-like numbers, then the smallest of those is the Murray number. So we get existence just by showing that there is one Murray-like number. Okay? So now what I'm going to do is I'm going to say, for any n, choose, what was my idea? So we need to get a perfect square. Now I don't know what n is, and I don't know its factorizations, but I know that if I were to say pair it with another n, I'd be all set. Now I can't choose the same n. But what I can do is I could say choose n squared. And then I'd pair it up and I'd get an n squared, and I'd have a leftover m. So what I'm going to do is I'm going to choose m equal to n cubed. Now we have to be a little careful. If n is greater than 1, so let's say for n greater than 1, we'll choose this. And then I'll show you what the answer is for, we'll work out 1 as a separate case. Then notice that n is less than, because we chose n to be not 1, n is less than n squared, which is less than n cubed. And n times n squared times n cubed is n to the 6th, which is just n cubed squared, a perfect square. Okay, so for n greater than 1, therefore we have a Murray-like number, and then by our observation, we have a Murray number. Now, since we would just want positive integers, now for n equals 1, just choose m equals 4. Then 1 times 4 is 4, a perfect square. So 1 has a Murray number. It isn't necessarily 4, because 4 is just Murray-like. But as long as we have one Murray-like number, we get the existence of a Murray number. No idea what it is, but we know there must be one. In fact, based on the second thing we have to prove, 4 must be the Murray number, because it's got to be at least n plus 3. Okay. So we've shown that Murray numbers exist. And what's the other thing? We have to show that a Murray number is greater than or equal to 3. Now, if you couldn't do that first bit, you would say, assuming Murray numbers exist, let's show that it has to be at least n plus 3. Okay? That way, if you get stuck, you can do the other half and still get some of the marks. But now we know, because of what we actually did, we now know Murray numbers exist. So to show the Murray number for n is at least n plus 3, we need to show n plus 1 and n plus 2 are not Murray-like. Because if they were, then they'd be smaller than n plus 3, and then one of the two of them would have to be the Murray number. Okay, so for m equal to n plus 1, we have n times n plus 1, and that would be n squared plus n. And you have to say, well, can this ever be a perfect square? What's the best way to do it? Well, let's suppose it were a perfect square. Then we'd have n squared plus n minus k squared is equal to 0. Quadratic here. So n is negative 1 plus or minus the square root of 1 squared minus plus 4ac all over 2. And 1 plus a square. So 1 plus 4k squared is not a square. So n is not an integer, let alone a positive integer. So that means you can't have n plus 1, because if you did, n times n plus 1 would have to be a square. We call it k squared. We could solve, and then, oh no, it all goes away. I should think there's got to be a better way to do that. Oh well. Doesn't matter. Now we just have one more. How about for m is n plus 2? So we got two possibilities. Either n times n plus 2 is a perfect square, or n times n plus 1 times n plus 2 is a perfect square. Now this first one here, I think we could probably do some quadratic stuff to show that doesn't work, but n times n plus 1 and n plus 2, we're a little stuck there, aren't we? Because that's going to be a cubic, and that's not going to be the easiest thing to work with. Well, in the meantime, let's take this one and expand it out. So n squared plus 2n minus k squared has got to be equal to 0. N is going to have to be negative 2 plus or minus square root of 4 plus 4ac. So there we go. All over 2 again. But this is 4 times 1 plus k squared. And since 1 plus k squared is not a square, then this whole thing is not a square. So n is not an integer. And of course, you'd probably want to use whole sentences there. But there you go. So now it's just this last one here, n times n plus 1 times n plus 2. Can that ever be a perfect square? So finally, suppose n times n plus 1 times n plus 2 is a perfect square. I don't actually know what I would want to do for this. Well, let's expand it out. We're going to get n cubed plus 3n squared plus 2n is equal to k squared. I don't know what to do here. It's all just about showing that this expression can't be a square. Well, let's think about maybe maybe if we work with even numbers here. So if n is even, so is n plus 2, and n plus 1 is odd. So both n and n plus 2 have to be, one of them is a multiple of 4 and the other one is not. So for any two consecutive evens, one is a multiple of 4, the other is not. And so you'd think, okay, one of them is going to be 4 times something, the other one's going to be 2 times something, but who says it's 4 times an odd? It could be 8 times something, and then you get 8 and the 2 combined to make it 16. Ugh. Okay, maybe even isn't the right approach. Maybe multiples of 3. No, because multiples of 3 would suffer from the same problem now, wouldn't it? Okay, hold on. Let's try something like this. Let P be a prime, and P divides n. So that means that n has got to be greater than 1. If this pans out, we're going to have to also show that 4 is the Murray number of 1, but that won't be too hard. So if P is a prime and P divides n, then if P is greater than 2, P doesn't divide n plus 1 or n plus 2, since n plus 1 minus n, well, since P would have to divide that, which is 1, or P would have to divide n plus 2 minus n, which would be 2, and so we'd have a bit of a problem. So that means, so n must be no, hold on. So, but P divides n, which divides, of course, this whole product. So P divides k. So P squared has to divide k squared. So P squared has to divide this whole product. But P can't divide either n plus 1 or n plus 2. So P squared divides n. So n must be some powers of 2, because we can't rule that out. So 2 to the something, it could be 2 to the nothing, times an odd square. But by the same reasoning, n plus 1 must also be 2 to the something, and one of these has to be odd, so one of these somethings will be 0, times an odd square. The same sort of, this works for all of them. We can do the same thing with n plus 2, but you can't have, I don't think you, well, by the same reason, it would also work for n plus 2, right? Okay, now if n is odd, then n equals an odd square, n plus 2 equals an odd square. But smallest odd squares are 1 and 9, which are 8 apart, not 2 apart. So that's impossible. If n is even, then n is 2 to some power times an odd square. 2 to the something times an odd square. And n plus 2 is 2 to the something times an odd square. But the difference has to be 2. So 2 is n plus 2 minus n, which is 2 to the something. There's a contradiction in there. I'm having trouble phrasing it. Basically, the point is, if you've got some odd squares, so our claim sort of is odd squares so 2 to some power of an odd square is at least 8 apart. Well, no, that doesn't work either. Geez, I'm getting stuck on this. Alright, maybe let's stop for a second and go back and see what have I been doing, because it seems kind of rambly. So, took a prime that's not 2, and so, you know, you must have p squared divides n, and you must have all the other p squareds divide n. So one of these here has to be a perfect square. And if it's n plus 1, then n times n plus... Okay, there we go. So let's get rid of all this. I have a feeling we were just going to sort of keep going on there. Okay, so n is 2 to the something times an odd square. By the same reasoning, n plus 1 is 2 to the something times an odd square. And n plus 2 is 2 to the something times an odd square. Okay. Now we've got at least one of n plus 1, or n plus 2 is odd. If n plus 2 is odd, if n plus 1 is odd, then n plus 1 is a perfect square. So if n times n plus 1 times n plus 2 is a perfect square, then so is n times n plus 2, which we know it's not. So we use the contradiction symbol. If n, or n plus 2, is odd, then n is an odd square, n plus 2 is an odd square, and now, but the smallest difference, in odd squares is 8 from 1 and 9. Okay, so therefore, if n is greater than 1, the Murray number, which I know exists, must be at least n plus 3. And now once again we come back to for n equals 1. n times 2 is 2, not a square. n times 3 is 3, not a square. 1 times 2 times 3 is 6, not a square. So 4 really is Murray number of 1, and that completes everything. We've shown that every number greater than n, the Murray number has to be at least n plus 1 or n plus 3, and for n equals 1 itself, we just exhaust them because it's quite easy to say 6 clearly not a perfect square. All right, so that did it. It took me a while, and certainly a little more effort that I had to put into this one than some B3s in the past on the intermediate. I wonder how people did this here on that one. I always wonder that, but especially if it gives me a bit of a challenge. Okay. It was an interesting concept. It took me a heck of a time to even understand what Murray number was. I wonder if their solution uses some Murray-like definition as well, because it was sort of a throwaway definition for me to sort things out at the start, but it really helped with those existences. The proof of the existence of Murray numbers, the proof that, in C part we can get an infinite number of those n's. Murray-like seemed to be a nice definition. They probably called it something else if they did use it. I don't know. You can click the link in the description, read their solution. I'd end up with egg on my face if they called it Murray-like as well, but yeah. Overall, I'd say it was a good 2016 paper, and that was the intermediate. I'm going to do the senior next, and hopefully it's just as good. So, yeah, if you want to, join me for that. Either way, have yourself a wonderful day.